Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Derivations, we'll be looking at the 7th chapter in the grade 12 syllabus for physics in CBSE. The name of this chapter is Alternating Current or AC Current, and in this chapter there are a lot of very important derivations and formulae that we need to keep in mind. So alternating current is a rare kind of physics because most of the time in the grade 12 syllabus you'll be learning about DC current and also static electricity. So over here in alternating current, the main difference is that the current is now oscillating with respect to time. So at some point in time it will be going in one direction, and at another point in time it will be going in the opposite direction. So therefore there are some technicalities and some formulae which differ in this chapter, and so therefore their derivations are extremely important. So today we'll be looking up with 3 derivations. They're pretty long and they're also very important, so be sure to take notes if you want to. The first equation that we should derive is derive the expression for alternating current through an LCR series circuit. L stands for inductor, C stands for capacitor, and R stands for resistor. So we need to find alternating current through an LCR series circuit. So what is the expression for that? So this is how an LCR series looks like. So now we consider an LCR series circuit of resistance R, capacitance C, and inductance L, with an output AC source of EMF E. So, and then we draw this diagram. So since this is an AC source, we represent it this way as opposed to a normal battery, which gives you DC source. So now let's consider E and I to be the instantaneous values of EMF and current respectively. Now VL, VC, and VR are the instantaneous value of voltages across L, C, and R respectively. So across the resistor, the voltage is VR, across the inductor, the voltage is VL, and across the capacitor, the voltage is VC. And accordingly, you can write VL equals I times XL, VC equals I times XC, and VR equals IR, the original Ohm's law. So in earlier expressions for AC current, where you had to find the alternating current passing through an inductor or a capacitor, you started off by writing the current in its standard form and then finding the EMF from that. Or actually over here we have to write the EMF first and then we have to find the current. So the EMF is written as E equals E naught sine omega t, and then you had to find the value of I. However, in an LCR series circuit it's just the opposite. What we're going to do is we're going to take I equals I naught sine omega t, and then from here we'll find out the value of the EMF. So we'll be doing this in many parts. So please stay attentive. The instantaneous EMF in an inductor will be given by the formula small e equals minus L times di by dt. This is present in the chapter electromagnetic induction. And potential difference, which I'm shortening down as pot diff, across the capacitor, that is given as V equals Q by C. Remember chapter 2, electrostatic potential and capacitance. And the potential difference across the resistor will be given by V equals IR, the Ohm's law, which we studied in chapter 3, current electricity. So these are the voltages and EMFs that are present here. So we take the net EMF in the circuit, net EMF in circuit, as the sum of potential differences across capacitor and across resistor. So basically the original EMF E plus the instantaneous EMF small e will be equal to VC plus VR. Now this we can write it down as capital E minus L into di by dt will be equal to IR, that is the value of voltage across the resistor, plus Q by C. So over here you can see you have di by dt, you will also have the current I and the charge Q. So we need to write these in terms of a phasor. So now what we're doing is we're going to take I as dq by dt. So from there you get dq equals I dt. The value of I is I naught sine omega t dt. The value of q will be the integral of I naught sine omega t dt. So I naught goes out, and then inside the integral it's sine omega t dt. So the value of q will be equal to minus I naught cos omega t divided by omega. So this is the value of the charge here. Now, since I equals I naught sine omega t, then di by dt will be equal to d by dt of I naught sine omega t dt. I mean sine omega t. So now you will get I naught times omega cos omega t. So now you know the value of I and the value of q, the value of di by dt in terms of phasors. So now we can substitute these in the equation for EMF. So let's consider this as, say, equation 1. So putting those values in equation 1, or we have to do a little bit of adjusting here, so let's not consider this as equation 1. Let's consider E equals L times di by dt plus IR plus Q by C as equation 1. And when we put the values in equation 1, put values in equation 1, we will get the EMF equals, that will be over here, since it's IR can be written as I naught sine omega t times r, plus, then we have the inductance, the instantaneous EMF, that is L di by dt, that will be equal to L times I naught omega cos omega t. Then we have plus q by c, which can be written as minus I naught cos omega t divided by c omega. So over here we have I naught, the initial value of the current, as common, so we take that outside. So then we have r sine omega t plus, over here you can see that cos omega t is common across the second and the third terms. So we take cos omega t outside, and you will get L omega minus 1 by c omega. So this is the equation for the EMF right now. But we're not over yet. Now what we do is we multiply and divide by r square plus L omega minus 1 by c omega, the whole square, all of that under a root. So we divide it by this value. So we multiply and divide by this value. So the equation of EMF now gets converted to I naught, then the multiplication under root of r square plus L omega minus 1 by c omega, the whole square. Then inside the bracket you will have r sine omega t divided by under root of r square plus L omega minus 1 by c omega, the whole square, everything under a root, and then plus L omega minus 1 by c omega in the numerator, and in the denominator you have the same term, so that is r square plus L omega minus 1 by c omega, the whole square, all of that under a root. So now what we do is we take r divided by the under root of r square plus L omega minus 1 by c omega, the whole square, all of that under a root. We take this as cos phi, and we take the other term, that is L omega minus 1 by c omega, the whole divided by r square plus L omega minus 1 by c omega, the whole square, whole under root. We take this as sine phi. So therefore the EMF now becomes I naught times r square plus L omega minus 1 by c omega, the whole square, whole under root. And then inside the bracket what you get is sine omega t cos phi plus cos omega t sine phi, which will now become I naught times r square plus L omega minus 1 by c omega, the whole square, and then you have sine of omega t plus phi. So sine A plus B gives you sine A cos B plus cos A sine B. So therefore the bracket now becomes sine of omega t plus phi. Now let's add a little side note. So using the dimensional analysis, we find that the under root of r square plus L omega minus 1 by c omega, the whole square, the whole under root, will have the same dimensions as that of resistance. So therefore we call this value as the impedance, and it is represented by the symbol Z. So therefore, we have E equals I naught times the under root becomes Z, and then there is sine omega t plus phi. So we now put E naught as I naught times the impedance, so therefore E becomes E naught sine omega t plus phi. So this will be the value of the EMF of an LCR series circuit when the current is I naught sine omega t. So we can find that in an LCR series circuit, the EMF leads current by phase angle phi, and which we can now find as tan phi equals sine phi by cos phi, which we now put the value as L omega minus 1 by C omega whole divided by Z, which was that under root, divided by R by Z. Now that is equal to L omega minus 1 by C omega whole divided by R. So this is the value of tan phi. So when L omega is greater than C omega, tan phi becomes positive. And when tan phi is positive, the value of phi will be between 0 and pi by 2. That means EMF leads current. When L omega is less than 1 by C omega, then tan phi is negative. That means the value of phi will be between minus pi by 2 and 0. So EMF lags behind the current. When L omega equals C omega, then tan phi is 0. So therefore, EMF, so when L omega is equal to 1 by C omega, then what happens is that tan phi becomes 0 because the subtraction becomes 0. So EMF is in phase with current. So it can have three cases. Either EMF can lead current, or it can lag behind the current, or it can be in phase with the current. It depends on the value of L omega and 1 by C omega. Again, L omega here is the same as XL, and 1 by C omega is the same as XC. Inductive reactance, capacitive reactance, respectively. So that was the way in which we derived the expression for alternating current in an LCR series circuit. It's one of the most important derivations in this chapter. Another important derivation is to find the resonance present in an LCR series circuit. So you need to derive the expression for resonance in an LCR series circuit. So now what we're going to do is we're going to take current in terms of the EMF that we just found. So I equals E by Z, that is EMF divided by impedance, which is equal to E divided by under root of R squared plus L omega minus 1 by C omega, the whole square. The entire denominator is under a root. So accordingly, with this equation, you can find that I is dependent on the frequency omega, the resistance R, the inductance L, and the capacitance C. So these are the values on which the value of current or I depends on. Now, the reason why it's dependent on omega is that XL and XC change with respect to omega. So when omega is low, so L omega is low, but 1 by C omega becomes high. And when the omega's value is high, then what happens is that L omega turns up high, but 1 by C omega becomes 0. So at a particular value of angular frequency omega, which we can call as omega naught, xl equals xc. So L omega naught will be equal to 1 by C omega naught. So at this point, the impedance Z will be equal to R square plus XL minus XC the whole square under root. So that will just become under root of R square because the difference will become 0. So that means the value of impedance will be similar to the value of the resistance. So when omega equals omega naught, Z is minimum. So the value of impedance is minimum and nearly equal to the ohmic resistance, that is R of the circuit. A series LCR circuit which admits maximum current corresponding to a particular angular frequency omega of AC source is called series resonant circuit. So when you have resonance, when you have a circuit at resonance, then what happens is that the value of omega will be equal to omega naught. That means the impedance will be low at its lowest point, so that means the circuit can admit maximum current. And the angular frequency omega naught is called resonant angular frequency. So case number 1, at resonance, which means omega equals omega naught, L omega naught is the same as 1 by C omega naught. So that means tan phi and the angle phi become 0. So the value of phi as well as tan phi will be equal to 0. Now what does this mean? The current and EMF are in phase. Next, the impedance Z is minimum, and the exact value will be Z equals R. So the value of impedance will be the same as the value of ohmic resistance. Now, another important thing is that the current attains maximum value, which depends only on the ohmic resistance R. So the value of omega naught can be written down as 1 by root of LC, when L omega naught equals 1 by C omega naught. And the value of frequency, linear frequency, can be omega naught by 2 pi. So therefore omega naught will be the same as 2 pi times F naught, that is linear frequency. So the value of F naught can be written as 1 by 2 pi times the root of LC, because we know that omega naught is already 1 by root of LC. So if you're drawing the figure for this, then you have current and then you have omega equals omega naught. So as the current increases, there will be this change in value as we progress through the circuit. So the maximum point for resistances R1, R2, and R3 always occur at omega equals omega naught, the maximum value of the current. After that, it starts decreasing. So this is the derivation with respect to the resonance in LCR series circuit. Now, another important derivation in this chapter is to derive the power in an AC circuit. So the power we're talking about is first instantaneous power, and from there we have to find out the value of average power. So power in an AC circuit is our expression that we need to find out. So the instantaneous power in an AC circuit is defined as P equals E times I, where E equals E naught sine omega t and I equals I naught sine omega t plus phi. So this is in any AC circuit, so don't worry about it. And now the value of P is equal to EI, because you will know that this will be the same formula that you have used in chapter 3, current electricity, where power was equal to VI. Here the V, that is voltage, is replaced by the EMF. Now, assume that the EMF and current is constant for the time dt. The amount of electric energy for the time dt is given by dW, that is the change in work done, equals EI times dt. Now the reason why this formula is used is that power is the change in work done divided by change in time. So at a particular point dt, the change in work done will be dW. So instead of power, we use dW by dt. So we take dt to the right hand side, so dW equals EI dt. So over here, what we're going to do is we're going to write E and I in terms of their actual formulae. So dW equals E naught sine omega t times I naught sine omega t plus phi, and then dt. So now what we're going to do is we're going to expand sine omega t plus phi. So E naught sine omega t times I naught, and then inside the bracket sine omega t cos phi plus cos omega t sine phi, and then dt. Now the sine omega t goes inside, so we have E naught times I naught, and then inside the bracket it will be sine square omega t cos phi plus cos omega t sine omega t sine phi, and then dt. So now what we're going to do is we're going to convert sine square omega t and cos omega t sine omega t. So sine 2 theta will be 2 sine theta cos theta. So therefore sine omega t times cos omega t can be written down as sine 2 omega t divided by 2. And sine square omega t can be written down as 1 minus cos 2 omega t divided by 2. So basically it's cos 2 theta equals 2 sine square theta minus 1. No, it's actually cos 2 theta equals 1 minus 2 sine square theta. So that's the actual formula, but then when you suit it to make sine square omega t on the left-hand side, you get 1 minus cos 2 omega t divided by 2. So dw is equal to E naught I naught, and then inside you have 1 minus cos 2 omega t divided by 2 times cos phi plus sine 2 omega t divided by 2 sine phi and dt. So as you can see, you have 1 by 2 on both the terms, so you can take 1 by 2 out. So E naught I naught divided by 2. And then inside you have 1 minus cos 2 omega t times cos phi. That will be equal to cos phi minus cos 2 omega t times cos phi plus sine 2 omega t times sine phi. So this is the value of the change in work done with respect to time. Change in work done will be E naught I naught divided by 2 times this whole bracket times dt, the change in time. So how about the value of work done? Work done will be integral of dw from 0 to say w. So therefore, if you take the definite integral on the right hand side, it will be from 0 to t. So E naught I naught divided by 2 times the dt, we can put it inside. So you have cos phi times integral 0 to t dt, because cos phi is constant, minus cos phi times integral 0 to t cos 2 omega t dt plus sine phi times 0 to t sine 2 omega t dt. So what we did is we took the dt into the bracket, so it goes distributed into all of the three terms, and then you integrate it with limits from 0 to t. So the value of work done will be this big equation. So why did we change it like that? So what happens is that over a complete cycle, the values of sine phi and cos phi, that is sine of phase angle and the cos of phase angle, become 0, because this alternating current is cyclic. So therefore, across a whole cycle, the value of sine phi and cos phi becomes 0. So therefore, the second term here, that is, so basically you have what happens is that we can write down integral 0 to t cos 2 omega t dt equals integral 0 to t sine 2 omega t dt equals 0. So basically this condition is put forth so that the cos 2 omega t and sine 2 omega t values become 0. So basically what happens is that the sine and cos functions become 0 as you go around the circuit, as you go around in this cycle. So cos 2 omega t dt and sine 2 omega t dt becomes 0. It's not the phi values that change, it's the omega value, so therefore that is now equal to 0. The integrals are now equal to 0, so the second and third terms are cancelled. The value of work done will be E naught I naught divided by 2 times cos phi times the integral of t from 0 to t, which is the same as work done equals E naught I naught t divided by 2 times cos phi. So this is the value of work done. Now the power average, the average power can be written as total work done divided by total time taken, which is E naught I naught capital T divided by 2 times capital T times cos phi. So therefore power average, the average power, will be equal to E naught I naught divided by 2 times cos phi. So the 2 can be written as root 2 times root 2. So therefore the power average can be written as the product of the VRMS values of both the EMF and the current. So the ERMS and IRMS. So ERMS times IRMS gives you the value of the power average. So average power is ERMS times IRMS times cos phi, where cos phi is referred to as the power factor, and the product ERMS times IRMS is apparent or virtual power. So this is how you can find out the power in an AC circuit. You found the general equation for power, then we found out the instantaneous version of it. So power here is dV by dt. So we can find only instantaneous power by multiplying E and I. And from there, after a long process of integration and substitution, we got the value of power average as E naught I naught divided by 2 times the power factor, which is the cos function of the phase angle. So that concludes this episode of Derivations. We hope you found this episode interesting. There are a lot of other videos on this playlist, so you can always go back to the playlist and approach more of our videos. For more of our useful and interesting content, don't forget to subscribe to our channel, which is once again Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.